So yes, hi again. I'm Marusa, and I would like to thank organizers for this opportunity to speak about our project. So I'm going to talk about a website that's dedicated to the nearby and young open clusters that are seen by Gaia. We've been working on this project with the team right there. And this is the address, but I should warn you, this is a work in progress, so the website is not active yet. But stay tuned because it's going to be online soon. Well, start. Okay, great. So yeah, open clusters have been fascinating objects in the sky, and people have been observing these for millennia. And they have been part of constellations in different cultures. So I found this very interesting plot from this wonderful website, Figures in the Sky. And this is a plot showing magnitudes. So bright stars are on the right and faint stars are on the left. And y-axis is showing the number of times a certain star appears in the constellations across different cultures. So for example, here on the left-hand side are faint stars, and the blue stars here that are marked are Pleiades. And it's clear that Pleiades appear in different constellations much more frequently than other stars with comparable brightness. And that's because they're significant in cultures and a very important role. We know that they have been using this to measure time, for orientation, and so on. So they have always have significant importance in cultures. And at the same time, we know that in modern astronomy, clusters are super important because they're benchmarks. We use them to fit the models for calibrations, initial mass functions, planets, low mass stars, and so on. And of course, there are many, many works on clusters, on discoveries, characterizations. This is just a very short list. It's not exhaustive. There are numerous other works. For example, yesterday, we've seen very nice talks about clusters. And also then we said, well, yes, we'll take Gaia data and characterize clusters ourselves. We'll find members using our own technique. We know that other works use very different techniques. But we use our own experiment method, which I'll describe later. Yes, so let's go to our clusters. We selected a list of 48 known clusters from the literature. All of them are younger than 1 gigayear because this is what we wanted. So at the moment, we're using Gaia EDR3, but our plan is to use ZR3 when it's available, so very soon, in a few weeks. And so we're using proper motions from Gaia EDR3 and distances from Baylor-Jones, which we know is based on Gaia. All our clusters are closer than 500 parsecs. We see distribution of distances here on the left-hand side. In our database, we do have stars that go a bit beyond 500 parsecs. That's because we have some clusters that are just below 500 parsecs. So we wanted to account for uncertainties and stars that are just at the limit, and we didn't want to skip any possible members. And here on the right-hand side, you see the distribution of our clusters in the galaxy, so galactic longitude versus latitude. We excluded galactic plane because things get a bit more complicated there. But as you can see, there are 3 clusters in the plane. So this is Alpha Perseus, and these 2 are IC2602 and IC2391. There are clusters with well-known age. That's why we wanted to include them in it. So this plot is from our website, which, so I'm talking about the website and everything, and at the end, I'll show it to you. This is a screenshot from the website from Aladdin. So as you can see, there's Milky Way, and the blue dots are clusters. This is interactive plot. You can rotate it and click on this, but I'll show you more later. And now what do we actually do? So we take Gaia data and approximate locations of known clusters, and then we derive new memberships with our method. We derive relative ages and luminosity functions. But now I'm going to focus mostly on memberships because this is what is going to be on the website. But just to mention, we also estimate tidal radii, and we cross-match the members with other photometric catalogs, such as 2MES, for example, to have as much photometry as possible available. And this is going to be on the website. So new memberships and photometry. And now I think I should tell you a bit more about our membership selection. So it's a kinematic selection. As I mentioned, it's a pyramid method. We use mostly 5D space or 6D if radial velocity is available. And so pyramid method is based on computation of the barycenter. So what we do, we have initial list of members that need to be selected very well. We compute the barycenter both in velocity space and in the usual space in Cartesian coordinates. And then the next step is to compare the velocity of the cluster with all the possible candidates of this cluster and compute the difference. And then obviously if the difference is small, then the star is most likely a member, and if it's big, then it's likely not a member. So it's a simple selection, but based on the kinematics. And this is how we got our members. And now I'd like to show you some results. This is my favorite cluster, of course, the Pleiades. The plot on the left-hand side, so it's called a magnitude diagram. So it's G minus RP versus the apparent G magnitude from Gaia, and it's a very nice HR diagram. And you can even see the binary sequence here. This plot is interactive, as I'll show you later, and you can zoom in, you can click on stars, you have an option to reverse the axis, have logarithmic scale, and so on. And you can select a different axis, what you want to plot, so it's very interactive. And on the right-hand side is 3D plot, which maybe it's best if I go in just show you how it works. So again, this is Pleiades in Cartesian space. So this is X, Y, and Z. And I think this is very nice representation. So the stars in the center are within 1 tidal radius, and the rest of the stars are within 3 tidal radius of Pleiades. And you can zoom in, you can rotate around. Sizes of stars are related to stellar mass, which is an estimate. So I think it's very nice visualization to play with this. And then if I go back, it works. Yeah, so I also mentioned that we are going to provide luminosity functions. So this is the preliminary plot for 3 clusters. And you plot absolute G magnitude, and this is a histogram, and we compare the clusters. And these are 3 clusters with very different ages. So IC2602 is about 50 million years. Pleiades is over 100 million years, and Hyades is old, I think it's 700 million years. And if you compare them, so for example, if you compare Hyades and Pleiades in this area here, so this is absolute magnitude between 10 and 12. These are cool stars. I think this corresponds to M dwarfs. And we see that Pleiades have relatively less M dwarfs than Hyades. And if you go to hotter stars, Hyades have relatively more hotter stars, and it's because of the evaporation of low mass stars. This is what happens with age, and this is what we want to study, how luminosity function is changing over time. But I should also remind you, this is really a preliminary plot. There's still much work needed. And I should also mention, so for IC2602, some of the stars in the cool end are still in the primary sequence, so actually interpretation of this peak is a bit more complicated. But yes, so yeah, speaking about the website, let's go and see it. Yeah, as I mentioned, it's still under construction, but we have some basic structure here. So this is the first introductory website with introduction of the contents. We're going to provide our paper here when it's ready and accepted, some acknowledgements. And then I think I'll go here and show you this promised all sky map. So I'm not sure how well you see there is a nice Milky Way, and you can travel across the sky and click on cluster. So you can see the name. So some data is not updated yet, but there's age, there's distance, and you can click on the cluster and it brings you to more plots. But before I do this, I'll go here, and there's our list of clusters. So in case you're wondering what clusters we chose, there's an entire list. and there's a table of basic parameters. Again, some things still need to be updated. But for example, now I want to show you again my favorite cluster, which is here. And this is what I promised you. So there's the name of our cluster, its coordinates, distance, galactic coordinates, and we're going to update this with proper motions we determine. And then there's interactive plot. So you can go and hover over the star and you see its basic parameters. And then you can actually go and click on them. And as you see here, so this is Aladdin inset, and it's connected to this plot. So if, for example, you wonder what star is, I don't know, this one here, and it's there, and you can zoom in, and this little faint star. And below you can also see what star is selected. So, and this is, you can copy this, some basic coordinates, and there is link to Simbad, to the star that you clicked. You can zoom in, and then you can choose other parameters. So I promised you color matrix diagram. So let's try to do this again. So G minus RP versus G. Now I need to zoom here. We still have some values that are a bit off because some stars, some values are missing in the catalog. So, oh, I need to reverse. But yeah, as you see, it's very interactive. You can play around. You can choose whatever axis you want to plot. And later we're going to add links to Vizier. So if you want to download data and then use it yourself in further research, there are going to be direct links there. Yeah, I think these are the basics of this website. And of course, we build this with the idea that well, there are lots of catalogs of clusters online in Vizier, but I think such an interactive website is a very interesting thing to do because it's very easy to use. It's just going to be there. And we hope that we're going to inspire not just professional astronomers, but also amateurs because it's very easy to use and a fun thing to do. So we hope that they will find this useful. Okay, thank you.
Any questions from the audience here? No, online?
The ages are from Qatar. From where did you take the ages?
So we are going to try to estimate them ourselves, mostly by, so we do plan to use rotation periods from tests as well, but the basic method is just relative comparisons. So we're going to plot CMDs on top of each other and just compare them. Oh, we think that this one is older than benchmark cluster, for example, because we need ages. The goal is not to have very precise ages, as precise as possible, but mostly just for luminosity functions. So we're going just to split clusters into 3 wide groups of age bins. So the goal is not very precise dating.
Very good.
Yeah.
Carmen?
Thanks for the talk and the website. Perhaps I missed, but I would like to know about the criteria. Why you choose 500 aspects, 1 gig a year?
So we wanted to.
But now we know about more than 2,000, so I have selected a few of them. What's behind that?
So 1 gig a year is because we wanted to study the evolution of luminosity function in the young age range. And 500 is because beyond this, we decided that, well, uncertainties grow big. And then we said, okay, let's go a bit closer. And even with 500, now I can tell you that with more distant clusters, well, uncertainties grow. And it's also the completeness, Gaia completeness issues in CMD. So it's, yeah, then problems occur when you go further away for what we want to do.
Other question?
You are corrected from extinction for every cluster. So you are considered time to select the cluster, outside of the reef. The distinction is very high, so it is over latitude, higher latitude, lower latitude. It's easier to consider that the distinction is good, and you can determine directly the distance, like the inverse of the parallax.
Yeah, one reason is extinction. And the other one is that if you go closer to the plane, then it gets more crowded and more complicated. And we said, okay, let's avoid these issues.
I understand that basically you want to reach the low mass regime, and then.
Yeah, I mean, it's not a very specific goal, but if we do, of course, we're going to be happy because we don't do any magnitude cuts. So we do parallax quality cuts better than 20%, but no magnitude cuts. So we can go a bit fainter than usual catalogs.
And this 20% parallax cut is on the basis of star by star or cluster by cluster?
Star by star.
Because in a given, if the error in parallax depends on the magnitude, so it means that actually we're not completely at the 20.
Yeah.
Okay, there's no more questions? No? Thank you, Marusa. Thank you so much for your talk.